All right, let's get started for the recording too. All right, so neural architecture search is exploding. And yeah, we have in 2016, there were just very few papers on neural architecture search. In 2017, that's where neural architecture search with reinforcement learning was published by Prof and Lee. And they used 800 GPUs for 2 weeks, which amounts to a cost of something like $60,000 US, just to do neural architecture search for a relatively small data set, such as CIFAR-10. But in the meantime, well, a lot of follow-up work, exponentially growing, has been devoted to make this much faster and more robust, etc. And that's what we'll talk about. So the outline is that we'll first talk very briefly about search spaces. Then we'll cover black box optimization methods, which, yeah, amongst others, the one by Prof and Lee, but those are slow. So then we'll talk about speed up techniques. Then we'll also talk about extended problem formulations doing joint NAS and HPO, and also neural ensemble search, and then also talk about benchmarks and best practices. All right, let's dive right into search spaces. So the simplest search space you could imagine is this chain structured space, where we have different colors denoting different layer types, and basically just for each layer, we choose what layer is this going to be. Is this a conf layer? What is the kernel of the conf layer, etc. But you can also have more complex search spaces with multiple branches and skip connections. The most popular type of search space these days is a so-called cell search space, where that was also used by Prof and a lot of other courses and Lee at a follow-up paper at CVPR. Here, they had two types of cells, one that preserves the spatial resolution and one that actually does downsampling. And then you can compose an architecture by stacking together individual cells. So for example, you take this normal cell, have it in the beginning of the network and in the end of the network, and in between you have a reduction cell. And well, in practice, they would have maybe stacks of 10 or 18 of these normal cells, and in between a few reduction cells in order to reduce the spatial resolution. A note here is that these cell architectures, so this cell and this cell, they share the architecture. So they have the same, yeah, exactly the same architecture that is bound, but the weights of this part of the network and of this part of the network are not shared. So it's just the architecture that is being repeated, but then this, once this network comes out, it's just trained as normal without any weight sharing. All right. So much for search spaces. There's a lot more on search spaces in our videos on the AI campus, but this suffices for this short tutorial. So let's talk about black box optimization. I mentioned NAS with reinforcement learning by Prof and Lee from 2017. This basically, well, so this yielded state-of-the-art results for CIFAR-10 and 10 tree bank, well, close to state-of-the-art for CIFAR-10. Basically, well, it had some reinforcement learner here that actually had a controller, which was an RNN. And the RNN would say, would define how to sample an architecture with a certain probability. So it would be an RNN that has as its output different probabilities over the different components of a neural network. And then you would sample a neural network and then train this child network with this architecture and get an accuracy R that would be basically the reward signal for the reinforcement learning agent. In their first work here, they used just reinforce. Later on, they used BPO. So basically, any type of policy gradient method you can run like this if you have a reward signal that you get approximate gradients for the reinforcement learner. However, well, this was this was very expensive. We get to this later. In a bit more detail, what they did is they had the architecture search wasn't actually very much of an architecture search. It was really more of a hyperparameter optimization here. They had the number of filters, the filter height, the filter width, the stride height, and the stride width. Those were the 5 choices that they would optimize for every layer. And this would repeat over and over again. So number of filters. This is number of filters for the next layer. And basically, they would have this, they would have a hidden state of their recurrent neural network that they would propagate, and then also an embedding of what the previous choices were. And so basically, you have this, this LSTM that has 2 layers of itself, and propagate these states forward. And at each time, the hidden state then would have an output. This is a probability distribution. So you sample the filter height from this probability distribution. Then you tell the next state what you did sample as the embedding, and continue like this. And well, this neural network, of course, has weights in here and there. And these weights can be optimized with reinforcement learning through policy gradient methods, or reinforce to actually then yield neural networks that give you good performance. The thing is that, well, this was first presented as something that's very special. You generate a string that represents an architecture, but really, if you look at it at the face of it, this is just a hyperparameter optimization problem. All you need to actually set is these 5 values for each of your layers. And so what they had in each cell, they had 5 of these so-called blocks where they made these choices. And then they had 2 of these cells. Each cell would have 5 times 5 categorical hyperparameters. And so there are 2 cells. So in total, it's just 50 categorical hyperparameters. And you can directly use hyperparameter optimization on this, or evolutionary search, etc. And that's precisely what was done afterwards. I'll get to that in a second, using evolutionary algorithms on exactly this hyperparameter space. Evolution, however, already has a much longer history for neural architecture search. So neuroevolution already was out in the 1990s. There, well, you would have evolutionary algorithms that would have mutation steps that slightly change an architecture by adding a layer, changing a layer, layer type, for example, or removing a layer. And these early neuroevolution algorithms, they often actually were used not only for the architecture, but they were also at the same time optimizing the weights themselves. And that has, in the meantime, found to be inefficient because, well, gradient descent is just really good at optimizing the weights of neural networks. But evolutionary search is still very good at optimizing the architecture of the neural networks. So the modern methods use neural architecture search by evolution to come up with the architecture, and then have a dedicated training module that just runs standard gradient descent. So it factorizes into these 2 components. And gradient descent is faster than evolution for training the weights of the neural network because it uses gradients, and evolution doesn't. And it's a very high dimensional space. So it's a smart idea to use gradients. So I mentioned that evolution was used directly on this hyperparameter space. This was done by Esteban Real, and actually from the same group at Google Research as Basin, together with Kwok Lee, and they compared apples to apples their previous RL approach, then evolution, and also random search, and showed that, well, RL is better than random search and evolution is better than the 2 of those. it also happened to be the case that evolution yielded models that had lower cost, but that was not part of the objective. That just happened to be the case. This paper here was also criticized afterwards in a blog post as, well, this cost something like $1 million to produce just a single plot because, well, it had to do all these individual really long training runs, each of which would cost something like $60,000. So, and I think they did 5 repetitions, so 15 times 60 is, well, I guess $900,000 US. If you were to run this on the cloud, of course, this ran on some servers at Google that maybe was cheaper for them. But it was important for the community because their code also wasn't available, so nobody could actually show that this RL wasn't actually that special. Bayesian optimization would have been better, evolution would have been better, etc. And they could do this apples to apples comparison, so it's very nice that they did that. All right, I just mentioned Bayesian optimization. Bayesian optimization has been used for neural architecture search also much earlier than also this NAS with RL. In 2013, for example, Bergstra et al. Optimized a vision architecture with 238 hyperparameters using TPE, the tree parson estimator, that's implemented in HyperOpt. And also the AutoNet approach was the first AutoDL system to win a competition dataset against human experts in 2016, also before the Soffenly paper. And this used the SMAC algorithm, which is just Bayesian optimization with random forests. And well, those of you who participated in the hackathon yesterday, this is precisely what SMAC did. A follow-up work of this AutoNet is AutoPyTorch, and I'll talk a little bit about this later. Usually Bayesian optimization in sort of 95% of the Bayesian optimization papers uses a Gaussian process model, not a random forest model. And well, in order to apply Gaussian processes here, you need to have kernels for neural architecture search. And there are a couple of papers. One early paper on an architecture kernel in 2013 didn't really catch on back then because NAS wasn't hot. But then in 2018, there was NASBot. This was a Bayesian optimization with optimal transport. And then in 21, NASBol, this was Bayesian optimization with a Weisweiler Lehmann kernel. And this is actually very efficient. So in something like 50 function evaluations or so, you can already get very good performance. You can also use Bayesian neural networks for Bayesian optimization. And one prominent approach that did that was this bananas algorithm that simply uses what's called deep ensembles. So you need an uncertainty estimate for Bayesian optimization, and this uncertainty estimate in bananas is just gained by training a neural network a couple of times and looking at saying the uncertainty estimate is how different the predictions of the individual neural networks are. If the individual neural networks predict the same for a particular architecture, then you're very certain. If they predict differently, then you're uncertain. And you can directly plug that into EI, and that's what bananas did. All right. Now, I'll talk later a bit about neural architecture search benchmarks, and in particular, NASBench 101. And on this, we actually compared these different algorithms and also saw that reinforcement learning is better than random search, and regularized evolution and Bayesian optimization are better than reinforcement learning. All right. So still, black box optimization is expensive. And the question is, can we do better? And that's what we shall talk about next in this module on speedup techniques. So we'll see 4 different types of speedup techniques. I can say already the meta-learning one and the multi-fidelity optimization one, they're exactly the same as you will see, as you would use for hyperparameter optimization. So there's really no difference. You basically just write your NAS problem as an hyperparameter optimization problem, and then, yeah, just apply the methods that we would have used for hyperparameter optimization speedup. The first two, those are special for neural architectures. So let's look at the first one on weight inheritance and network morphisms first. So a network morphism is an operation that changes the network structure, for example, from this one to this one, but does not change the modeled function. So for every input that you would give to this neural network, you would actually want to preserve exactly the output that the neural network gives you. So sorry, if the input goes in here, and the output, input here, output here, I guess, in this case here. If you have a layer in between that's actually just an identity, then the function will not actually be changed. So you change the network structure, but you don't change the functional mapping at all. And this is useful in neural architecture search because it allows you to do very cheap moves in architectural space and gives you a pretty much pre-trained model. So you can have this architecture, train it, it's pretty good. Then you just add a layer that's an identity mapping. And then you have this architecture, which has the same performance as this one because, well, for every input, it gives you the same output. So it also has the same performance. But then this is a different architecture, and it's a pre-trained version of this architecture. And now you can just do a little bit of gradient descent to also optimize the weights in this blue layer to not be an identity mapping anymore. And then typically you get a little bit better performance. So to demonstrate how this works in an algorithm, so you would have some model that's here, two larger layers, two smaller layers of different types. And you can apply network morphisms to, for example, make this layer here a little bit wider, add a layer, maybe add a skip connection somewhere. And the performance of these models is still going to be exactly the same as here because, well, these are network morphisms. So the function has not changed, the performance has not changed. Then you do a little bit of training on each of these, and that improves the performance on some of them more than on others. And a simple technique would be to just say, well, I'll take the best one that came out and make that my new model and iterate. And that actually already allowed architecture search in 12 hours on a single GPU. So much, much faster than previously. However, this has one problem, namely that the architectures grow larger and larger. A network morphism can only make your network larger. It can't make it smaller because if you make the network smaller, then you can't have exactly the same functional mapping. You could do this approximately, but you can't do it perfectly. And so you don't want your networks to grow larger and larger. You also want to have small networks that do well. That's why we have this follow-up on efficient multi-objective architecture search, where we traded off the network size versus the error, maintaining a Pareto front of the two objectives. So we started with some set of architectures that gives you this Pareto front. So there was an architecture here and there and there and there and so on. And here there's a number of parameters, and here's a validation error. And you want to move this to the left, reducing the validation error, and downwards, reducing the number of parameters to achieve a certain validation error. And over the course of the run of this evolutionary method, that's precisely what would happen. This Pareto front would move left and downwards to, after 100 generations, give you this pretty dense Pareto front here. And this is implemented in this Lemonade algorithm with Lamarckian evolution for multi-objective neural architecture design. This already actually performed better than this NASNet, or better or similar to this NASNet, but most importantly, 35 times faster, and would also give you transfer to other architectures. So you can run it in the cell search space. That is something where the cell search space is really good for. You can optimize these cells for something like CIFAR10, and you can then take these cells and directly move them over to a different data set, such as ImageNet, and typically you still get better performance. Of course, the correlation is not perfect. Sometimes you get better performance for CIFAR and a little bit worse for ImageNet, but typically they're correlated quite strongly. All right, so that was the part on weight inheritance and network morphisms. And next, we'll talk about weight sharing and the one-shot model. So the most popular or most prominent, best known method for working in the one-shot model is called DARTS, the differentiable architecture search. And so the motivation for this is as follows. So you're going to have here in each of the nodes, you have tensors, and on the edges you have operations such as convolution or max pooling. And on each of these edges, the question is, okay, what operation do you want to use there? And so you could treat it as this discrete problem, and then each of these question marks would be a categorical hyperparameter, and do your search like that. But of course, as we saw before, that's expensive. So what DARTS does instead is it replaces the single edge here by multiple edges, in this case, 3 different edges. Each of these edges has a different operator, and then you would simply sum the results of these operators to get into this tensor here. So and you also weight them. So to show this formally, you have different operators, these O of x here, and there's a set of operators, capital O here, and a mixed operator going from tensor I to tensor J now would simply give you a weighted sum over these operators in O, and each of these operators would have a weight that's called alpha sub O here. So you have a weight, for example, for this 3x3 convolution, one for this 5x5 convolution, and one for this max pooling. And so you carry out those operations, you take the results, you multiply them with the weight of that particular operation, and then sum them up to give you this tensor. And the advantage of that is that now we have this continuous architectural weight alpha for every operator. And since that is continuous, you can actually do gradient descent on it. And what you can do is solve a so-called bi-level optimization problem. So you try to find the alphas such that when you optimize the weight for that particular alpha running SGD, by running your standard SGD loop, you minimize the validation loss for your alphas. So let's say this again. Optimally, in this inner problem, this W star of alpha is, well, a converged version of SGD that's just minimizing training loss for this particular architecture. And that's we're going to call the optimal weights for this architecture alpha. And then we're going to compute the validation loss of this particular architecture with these particular weights. And we're looking for the alpha such that if you optimize the weights for that alpha, you get good performance. Now, of course, this is not necessarily cheap the way I just said it. That just says, well, this inner problem, you need to run SGD to convergence. That's not what DARTS does. Instead, what DARTS does, it just does a single update step here, a single gradient descent step on the training loss, and then it does a single gradient descent step on the alphas with respect to validation loss, and it iterates those. You could also just do one step here and then do a full run of SGD here, but that would just be slow and expensive. And it so happens that if you just do a single step of gradient descent here, that is already giving you very good performance. There's no convergence proofs there that actually would work, but in practice, it actually does work. So the training and validation losses are going down. So what this yields is a set of alphas for each of the operations, where some of the alphas tend to be stronger than the other alphas. So you would then say, well, here I really kind of like this, I don't know, this 3x3 convolution with a high alpha of 0.8, and the others maybe have 0.11 and 0.09. So you kind of downweight them. And then the final step in DARTS is to drop all the operators that have not the highest weight on this particular edge. And actually, you also drop some path entirely. All right, and then basically you have something that is a discretized version that has only individual edges, and then the memory requirement is also smaller. For this one-shot architecture, the memory requirement is higher because, well, there you have 3 different operators, each of these with different weights. And so the memory requirement here is 3 times the memory requirement of the discretized architecture. Or the discretized architecture, if it even drops this one, then it's even less than 3 times the memory complexity. All right, so maybe first some pros of DARTS. It actually works. In some cases, we use it for actually tuning a vision pipeline for getting depth from stereo. That's just a computer vision problem you don't need to know much about. You have an image from a left camera and an image from the right camera, and from that you can compute the depth. And this auto distnet actually worked quite a bit better than the previous distnet, which was developed in the computer vision group here in Freiburg by Thomas Brox, with several PhD students having worked on that for several years. So they really worked on this. They were world experts on this. They had the best results on this. And nevertheless, using DARTS and architecture search, we could still together find an architecture that yielded better performance on, well, this prominent Intel dataset. And the runtime here is only a 2- to 3-fold overhead over training a single network because, well, you're only doing these iterative update steps. You do 1 step here, 1 step here, 1 step here, 1 step here. Maybe you need to run a few more steps than you would have to run otherwise. But there is not this step where, well, this training here takes as long as a normal training, and then you do this thousands of times that you would have in the black box optimization way. All right, so that's a pro of DARTS. A con of DARTS is that it often fails horribly, returning really degenerate architectures such as these ones that only have skip connections and nothing else but skip connections. And we actually showed that, my PhD student Arbor, who is going to run the hands-on later, showed that in an oral at iClear last year. And this was consistent across 12 different NAS benchmarks, so 4 different search spaces, 3 different data sets. It just always yielded these skip connections. And the reason behind that is, well, it's not that the optimization is a problem. So this iterative optimization is actually fine. The one-shot validation error over time is going down for all of these different search spaces. That's not the problem. But the problem is that the curvature increases. So we're getting to points in the space where just moving the alphas a little bit gives you actually much higher validation errors. And we see this here as there's a dominant eigenvalue as a proxy for the curvature of the space. This is for the alpha space. In the beginning, this is small, and over time, as the number of search epochs increases, it goes up and up and up. Meaning, if we move a little bit in the alpha space, we actually get a large change in the validation error. And This is a phenomenon that's also known in standard gradient descent training. That's this phenomenon of sharp local minima. If the training and the test set are slightly different, then this can also give you poor generalization performance. Here it's doubly bad because, well, in the end, we have this discretization step. And this discretization step, well, that is actually a fairly substantial move in architecture space because it just drops these parts of the architecture. So we do move, and a move in architecture space gives us poor performance, and that's precisely what happens here. Our test error over time, actually in the beginning, it goes down, and then as the search epoch increases, it tends to go up a lot. And yeah, gives us these very poor architectures, in this case, all skip connections. What can be done about this? Well, we can fix these sharp local minima by doing more regularization. And there's different ways of doing this regularization. One option is, well, just do early stopping. Here we say if we would stop here, we'd actually be pretty good. Another option is to do L2 regularization, for example, of the inner objective, or also scheduled drop path, which is kind of similar to dropout, but in architecture space. And this regularization avoids this high curvature. So you also don't have this going up over time anymore, and leads to much better performance. Funnily enough, darts on the Dart search space on CIFAR 10 actually still was very good. That was the one data set that was used in the darts paper to show performance. But if you just go to CIFAR 100 and run the original thing, it already is poor. And this robust darts version would actually give you much better performance than the original darts. And there's lots of follow-up papers that are regularizing differently. So for example, this perturbation-based regularization at ICML last year, or also this, this follow-up here that looked at the final architecture selection process. It was actually best paper at ICLR this year. All right, so much for rate sharing. And yeah, next I'll talk about meta-learning. This is going to be simple because, well, we saw before, we can formulate NAS as HPO. And we saw yesterday very briefly, admittedly, that you can use meta-learning as a speed-up technique for HPO. And there is dozens and dozens of papers on this. And we can directly apply these methods in order to do meta-learning as a speed-up technique for NAS. This hasn't, however, been done very much. In a nutshell, it has been done for HPO a lot, and for NAS, it's really something that, more work needs to be done. And Thomas Esken will talk about meta-learning for NAS a lot later on. But so in a nutshell, how would you do this? So you would take into account previous runs of previous architectures on other related data sets. And then you would either initialize your search with previous high performance architectures, so architectures that did well, maybe on average across the previous data sets, or you would fit a model. And for example, in Basin Optimization, you could warm start your model by taking into account how well the architecture performed on the previous data sets. Alternatively, you can also combine meta-learning with a one-shot model by actually doing meta-learning on the alphas of darts. And that is what Thomas Esken will talk about later, so in a couple of hours. All right, so much for meta-learning. The next part is multi-fidelity optimization. And here again, this is very related to what you saw yesterday. So the key idea, again, of multi-fidelity optimization is to use cheap approximations of your black box. And I think maybe yesterday you didn't talk about deep learning so much, but the main idea about these multi-fidelities is that you can choose which cheaper approximation you want to use. The main thing you want is that the performance on your cheap approximation actually correlates with the performance on the black box. And the performance on the cheap approximation doesn't necessarily need to be very good. It can be pretty crappy as long as sort of the methods that do best for the cheaper approximation also do best for the expensive black box. Then you can basically do a lot of the optimization on the cheap approximation and then move the results over to the expensive one. So how can you get these cheaper approximations? Well, you could use a subset of the data. You could use fewer epochs of SGD. You could downsample your images in object recognition. You could use shallower networks with less layers or slimmer neural networks with less weights per layer. In Bayesian deep learning, you could do shorter MCMC chains. In reinforcement learning, you could do fewer trials. So there's really many, many different ways in which you could do that. And it makes sense to think about, for a particular application, where the rank correlations between what works well on the cheap approximations and what works well on the expensive black box might be the largest. And you could also potentially run some initial experiments, but technically that should then be counted as already part of the x-axis. So yesterday you saw this approach called successive halving, and hyperband you also saw. The simplest method here is successive halving, which is, say, at each step, just throw away the worst half of the of my training runs and only continue the top half, and that gives you pretty good performance for an amortized, pretty cheap runtime. There is a lot of many more complex methods. So combining this with Bayesian optimization, for example, fitting a model that takes into account not only the hyperparameters or architectures, but also the different fidelity levels, and actually fits a model across different fidelities so that you can predict which method will actually work well with the highest fidelity. And you can also define acquisition functions that would consider information gain, for example, on the highest fidelity by running something on the cheaper fidelities. These methods are very promising, but they also tend to be somewhat brittle. And so in our experience, we did see a simple combination of successive halving or hyperband and Bayesian optimization to yield better performance, in particular this Bob algorithm you saw. And we also used that in this paper here, where we ran darts first with the collaborators in the computer vision group here to get a 10% improvement, but then actually doing hyperparameter optimization afterwards yielded another 10% improvement. So these two are definitely complementary, and I would recommend not only doing architecture search, but also definitely doing hyperparameter optimization for a domain of interest. All right. Yeah, you also yesterday saw the DEP algorithm. This from our group kind of replaces Bayesian optimization with differential evolution. So usually evolutionary algorithms require too many function evaluations to be competitive with Bayesian optimization. And that's why they're not that popular for HPO. But actually the funny thing is, in multi-fidelity optimization, we can typically afford more function evaluations for the cheaper proxy. So for the expensive function, we still can't afford a lot of function evaluations. But if we have a proxy that's maybe 100 times cheaper than our black box function, then, well, in the end of the day, we'll actually do more function evaluations on the cheaper proxy. And that sort of shifts the sweet spot over to evolutionary algorithms to actually work better in a certain, in a fixed time frame. However, as Mario said yesterday, our other follow-up of Bob is actually using Bob with random forest, not with TPE, and that also does much better than the original Bob. So this Bob with random forest and DEP do about similarly. Great. However, if you do have lots of parallel workers, then the current implementation of DEP is actually much better suited than the current implementation of Bob and SMAC, because, well, the parallelism in SMAC isn't quite as good yet as for this differential for DEP. but that's probably something that can be fixed relatively easily. It just needs to be done in SMAC. But if you need to run a hyperparameter optimization method today and you have lots of parallel workers, then I would prefer DEP over SMACBOB, but that may change in a couple of months. All right. So much for neural architecture search. I would now talk briefly about some extended problem formulations of neural architecture search, namely joint NAS and hyperparameter optimization, and then searching not for a single architecture, but for a whole ensemble of neural architectures that do well together. So let's talk about joint NAS and HPO first. I already mentioned this AutoNet approach that we did back in 2015, and this really just does basically Bayesian optimization on a formulation of NAS as HPO plus also the hyperparameters added. So it's just an extended hyperparameter space that has both NAS and HPO in there, and that already in 2015 worked quite well. For example, in the first AutoML Learn challenge, there was a data set that had about 55,000 data points, 5,000 features, 18 classes, and AutoNet got an AUC of 0.9, and the best human team actually only got 0.8, despite the fact that they had 2 months to work on this data set. And they could have done this manually, but didn't. And we ran AutoNet on, I think, 8 GPUs back then for 1 day, and it already did better. So it's an existence proof that, well, automated tools can really help to improve performance also over deep learning experts. Nowadays, what we have is AutoPyTorch. Back then, AutoNet was actually in Keras. Back in the day, this was the standard framework. That's a long time ago. Actually, no, it wasn't Keras. Sorry, it was even Theano, even earlier. So we still do joint architecture and hyperparameter optimization, but now we also do multi-fidelity optimization, and we also do meta learning to warm start across datasets, both in the hyperparameter and in the architecture space. This is of course open source, and we'd be very happy if you contribute. The search space we used here, so in AutoPyTorch, so far we focus very much on tabular datasets because the space is less crowded in a sense than, for example, CFAR and so on, where you also need a lot of resources to compete. But for tabular datasets, so we used an architecture that's basically like a ResNet, but a shaped version of a ResNet, where we parameterize things like the number of blocks and then the number of groups of these blocks. And you can have also the number of units and whether you use dropout or not. Shake, drop, and shake are various regularization techniques that are on the architectural level. So we had roughly a dozen architectural choices and roughly a dozen hyperparameter choices there. And the multi-fidelity optimization was simply with Bob, using a budget as the number of SGD epochs. And this couldn't give us a huge speed up, right? Because the minimal budget here was 12, the maximal 50. So this could only possibly give us a speed up of a factor of 4 if we have perfect correlations. But actually this factor of 4 we did sometimes get. This is, this here is, these plots here are for the warm starting, which did turn out to be much more important for AutoPyTorch. So we initialized the search with complementary configurations that covered previous data sets, and this would give these up to 100-fold speedups here. So this was this approach of covering previous data sets. We could also just initialize with the single architectures that work best on individual previous data sets. That wouldn't work quite as well, but rather it was important to pick architectures that work well on average across many of the previous data sets. All right, yeah, and this worked well in the comparison to AutoKeras and AutoSKlearn. This was AutoSKlearn 1.0. There, the story is also, of course, changing because AutoSKlearn 2.0 is also very good. And yeah, we have further evaluations going on also on the AutoML benchmark and with AutoGluon comparing to them. All right, this isn't, in terms of the methods, this isn't only restricted to tabular data. You can also run this on image data, and we've actually run it on NASBench 201. There's 3 data sets in NASBench 201, so we really only would have 2 meta-training data sets to transfer to the 3rd one, and nevertheless, we could actually get very nice performance. You kind of don't see it very well here, that the purple is much better than the other ones, but the x-axis here, this is a factor of 100, and so you would have almost 100-fold speedup sometimes, 10 to 100-fold speedups. And actually, it was so fast that it was competitive with gradient-based NAS, so it was 4 times faster to reach 90% performance on CIFAR 10 than GDAS, which was the best one-shot method in the NASBench 201 paper, much better than Darts. Darts actually diverged on this space. All right, so, well, in a nutshell, there I would say multi-fidelity meta-learning, that's sort of a stable, it's a very stable method. It typically, I would say, if you really tune your one-shot model method and it does converge, it's probably still a bit better and probably still a bit faster than multi-fidelity meta-learning. But in terms of robustness, I think, we're clearly multi-fidelity meta-learning would be preferable over the one-shot models. All right, so then let me move to this neural ensemble search. There, the motivation is that ensembling often improves the performance of neural networks. And in particular, this deep ensemble approach that I mentioned very briefly earlier in the context of bananas actually has been shown to yield very good predictive uncertainty estimation and robustness to distributional shift. So these deep ensembles, to recall, are really, really simple. They just exploit the randomness in SGD to run into different local optima. And so you, for example, just run 5 neural networks with a different random seed, so different random initialization, and then different trajectory of SGD. They run into different local minima, and then you average them. And your uncertainty is the uncertainty of how well do the 5 predictions agree. And that actually gives you very good predictive uncertainty and also robustness to this distributional shift. So distributional shift, I have this later. Here's distributional shift. So you have, for example, some corruptions of your data. So your training distribution is shifting. For example, in this data set here, by adding noise, various different types of noise for these, in this case, validation corruptions, and then your test set would have yet different types of corruptions. And actually, if you have these deep ensembles, they are actually quite robust to these different corruptions. So that's what I meant here. And well, another type of the motivation, part of the motivation here is that diversity among the base learners' predictions is actually key for good performance of ensembles. And usually in the literature before, this diversity was only gained in the weight space. For example, deep ensembles would give you different different weight vectors, but they would always use the same architecture. And well, whereas people in practice on Kaggle and so on have previously definitely looked at using different architectures and exploiting the diversity in that part of the space. And so here we actually used NAS in order to search for good base learners that would combine nicely in order to have high diversity, but also be good for each of them in order to actually get good ensemble performance. And so we didn't actually directly optimize for diversity. We just optimized for best ensemble performance, but that implicitly actually gives you diversity, because if you don't have diverse architectures, then you don't get as good performance. And yeah, this is a plot that actually looks at different metrics. So for example, it looks at the error of your ensemble, the ensemble negative log likelihood, and your expected calibration error. And there we have, so the deep ensemble approach is here in yellow. And so there the expected calibration error and the ensemble negative log likelihood are actually higher than those of these neural ensemble search methods, despite the fact that we actually used the best architecture here in the search space. So this was run on Naslib 201, which you can enumerate exhaustively, and we used the best architecture and 3 different weight vectors for it. The 3 ones that are in Naslib 201, and you compared that to neural ensemble search that had just 1 weight vector, but for 3 different architectures, so the same memory complexity. And this NES is just better in all of these different metrics, except the one that is the average base learner negative log likelihood. So there, well, the deep ensemble, because it's based on the best architecture, each of the individual performances of these base learners are actually better for the deep ensemble. And the neural ensemble search, well, wants diversity and therefore picks different architectures that individually are actually worse, but then in conjunction with each other, they're better than the 3 instantiations of the best architecture alone. All right. So here's a picture showing that different architectures really do make diverse predictions. So here on the left, we have predictions from 5 different architectures, and you see that the predictions of each of the individual architectures really cluster together. Whereas on the right, we have predictions of the base learners and ensemble, here found using neural ensemble search, and here just the ones of the deep ensemble of the optimized architecture. So the predictions are much more similar for a given architecture than they're across different architectures. And yeah, so this neural ensemble search then also gives you very nice performance under data shift on these data sets, CFAT10, C, ImageNet, C, and so on. Yeah, I'm not going to go into the details of this plot. All right, and that brings us to the last point I want to talk about, and that's benchmarks and best practices. So I talked a lot about NAS. It seems all super exciting. Maybe you've gotten a little bit worried about this failure mode of darts, but otherwise it sounds really cool and like the thing that definitely everybody should be using. However, there are some childhood problems that the NAS literature had to overcome. One of them is that, well, this very nice paper here, NAS evaluation is frustratingly hard, from 2020, actually showed that the training pipeline matters much more than the architecture. So they took the popular Dart space and took 5 different architectures that yielded some performance changing by something like 0.5%, and then changed the training pipeline to first include auxiliary towers. That didn't improve much. Then they included drop paths, which is this regularization performance, regularization approach. Performance jumped by about 1% already. Then they added cutout, another regularization technique. They added both cutout and drop paths. So this here was just cutout alone, and this here is cutout and drop paths together. And then, yeah, also had more channels and auto-augment and more epochs and so on. And then in the end, they actually moved from this performance, 95%, to up here, 97.5%. So really 3.5% just by changing the training pipeline and 0.5% by changing the architecture. So that shows that really different results are very incompatible, very uncomparable when they're based on different training pipelines. And this is the sort of table that you see in many NAS papers, where, people maybe report the number of parameters of an architecture and then their performance. But I would like to impress on you that this is really not the way to go, because each of these individual papers used some different training pipeline. In the early days of NAS, these training pipelines were not available. They're just, Google, for example, never released their training pipelines for NAS by reinforcement learning. So there is no way anyone could reproduce this. Anyone could try to, even if they have a better meta algorithm, a better NAS algorithm, they couldn't show that it's a better NAS algorithm because they wouldn't have the secret sauce of the training pipeline and so on. So different papers use different training code, different search spaces. Also, if you have an awesome search space that's basically just focused around an awesome architecture, it's easy to find a very good architecture. Different evaluation schemes. So all of this was very incomparable. And that was actually the main reason that I got into neural architecture search benchmarks. We created this first Tabula NAS benchmark in order to get rid of all these different sources of incomparability, but actually have something where, if you do better on the Tabula NAS bench, then there's, it's a direct apples to apples comparison. So the motivation for Tabula NAS benchmarks was that, NAS algorithms require very long runtimes, as we talked about many times before. And then, if a single run takes 2 weeks on 800 GPUs, you're also not going to run a lot of competitor algorithms. Nobody in their right mind could make you do that. But so really the science goes out of the window. You can't do repeated runs, you can't do statistical tests, and this has haunted the community for the first couple of years. Now with Tabula benchmarks, what are they? Well, so what you do is you actually store the performance of this expensive step of training the architecture and evaluating it on a holdout set in a table. And offline, you do this a lot for every single architecture in a search space. You store the result in a table. And then online, when you actually want to use it, you replace this slow step of training your neural networks by a table lookup. So when we say we run regularized evolution on NAS Bench 101, this means regularized evolution says, I would like to evaluate architecture X. We look architecture X, okay, we'll look in the table, you get this performance. And it takes a millisecond rather than taking 5 hours to train on a TPU. And then you can, of course, run your regularized evolution thousands of times, do all kinds of statistical tests, ablation studies, and so on. You can do this on a laptop, and it really enables proper scientific research and fair apples-to-apples comparisons because, nobody gets to actually change this training pipeline because, the results of the training pipeline are in the table, and you can't change the table. NAS Bench 101 in particular, we had 423,000 architectures evaluated on CIFAR 10. This took 4,000 TPUs for several months. And that's why I could, of course, only do this together with Google. And thank you very much, Google, for providing these resources. And while we had to run this 4,000 TPUs for several months, nobody has to ever run this again. And it has been used in many hundreds of papers and has saved, in an amortized fashion, has saved probably hundreds of thousands of TPUs for years. So definitely this one-time compute has been extremely useful for the community. All right. So and this then enabled comparisons like this. And for example, it allowed us to show that SMAC, which was published in 2011, outperformed RL, which was published in 2016 for NAS. And I kind of thought that this would happen when the initial paper was released. But yeah, I asked in the talk, but have you compared? But of course, they're like, well, it's super expensive. No, we haven't compared. And now we can actually do these comparisons and do proper science. This Tabula NAS benchmark methodology has really caught on. So there's lots and lots of Tabula NAS benchmarks these days. NASBench 201 in particular is very popular. NASBench 101 is still popular, but it's not so nice for one-shot methods, and NASBench 201 is nicer for one-shot methods. Also, there's an extension of NASBench 201 that also looks at the impact of architecture size. Hardware costs are being benchmarked a lot. So there's this lab bench and hardware-aware NASBench. Then NAS benches are also being created for automated speech recognition, for NLP. Nothing based on transformers yet. It's sort of a little too expensive, but it's on the horizon. A lot of people are interested in it. However, there's still one problem. All these NAS benchmarks are far too small to be realistic. So in NASBench 101, we had 423,000 architectures. It's kind of ridiculous to think about so much compute, but still 423,000 is nothing compared to the typical search spaces of that you use in neural architecture search. For example, darts are something like 10 to the 18, and there's just no hope at all to come up with tabular benchmarks of that size. What is more, actually, also this paper in 2020 has shown that local search was actually state of the art for these small tabular benchmarks, but was actually poor on large spaces for relatively small runtime. And so that goes to show really we need to look at larger spaces, and we need to have some sort of benchmark for the larger spaces. And the solution there is to actually work with surrogates. The NAS surrogate benchmark methodology would just say we evaluate a subset of architectures and fit a model to those, and we use these model predictions in lieu of the real or tabular benchmark. And of course, there have been many previous works that use the surrogate model to predict in architecture space. For example, all the Basin optimization methods that I talked about. And also there's work on predictor-based NAS. But here we're using the surrogate model not to speed up the search, but actually to define a benchmark. So we would basically replace the step where you train and evaluate your architecture by just asking a surrogate model for the performance of this, just like you would ask a table in a tabular benchmark. And the nice thing is that any improvements in surrogate modeling for optimizing the search time, because you have a better model, will also improve these surrogate NAS benchmarks to be more and more realistic. Now, you might think, well, the surrogate benchmark idea is nice, but you might actually incur a lot of error and have unrealistic benchmarks. It so turns out that actually these surrogate benchmarks can be more accurate than tabular ones. That's sort of confusing at first, because a tabular benchmark, you have evaluated everything, you're done. But actually, well, these individual evaluations have error due to the noise of SGD. And so many NAS benchmarks actually quantify this error with 3 to 5 repetitions for some, at least for some of the architectures. And from a machine learning perspective, what this would mean is this tabular benchmark predicts a noisy function f of a by evaluating at exactly a few times and then returning the mean. And that makes an independence assumption, just not using the data for similar architecture as a prime. And a good model should actually do better than that by taking into account the other 423,000 architectures. And this is actually what happens in practice. So here for Naslib 101, we have the mean absolute error that's being made, and this is the error made by the table. That's the error due to the noise of SGD. And the surrogate benchmark, actually, if you train it on very few architectures, makes huge errors, but there is this crossover point here at actually around 20,000 architectures used for training. When you use those, or when you use more, then the prediction error for new unseen architectures, for new unseen seeds, is actually lower than the error you make when you look in the table for that exact architecture, but for a different seed. So you can exploit that you have seen similar architectures and can smoothen in that space, and the error of SGD is actually higher than the error that the model makes. And so that puts some rest to the worry that the surrogate model might make a lot of mistakes. So we created then a surrogate NAS benchmark for the Dart space, which has 10 to the 18 different architectures. We evaluated 50,000 different architectures in that space. We got them by using different optimizers to kind of cover the good part of the space with all kinds of different optimizers. And then we evaluated a broad range of different regression models. The best ones that turned out to be gradient boosting or graph convolutional neural networks. And again, the estimation errors also for the Dart space were lower than those of a single run of SGD. You can then benchmark NAS methods on this surrogate NAS benchmark on Dart. So here would be a run on the true benchmark. This is one run of these individual methods because this takes something like a GPU year here. And on the surrogate benchmark, of course, you can run a lot of different runs, and that's why these curves here are much smoother, and the qualitative trends are preserved. So, for example, this regularized evolution takes a while and then actually gets good performance. Same here. Bananas from the beginning on or from fairly early on does quite well, and yeah, things like that. And random search, is always amongst the worst. I already said this. And so you can now actually do benchmarking on these large spaces by building a surrogate benchmark for these large spaces, and then can compare arbitrary methods on there. So wrapping up this part, we also came up with a NAS best practices checklist together with Marius. Seeing all these issues of people using different search spaces, using different code, not releasing their code, and so on. So we said definitely release your code. And releasing your code, many people say, we're releasing code, but all that they did is open source the final architecture found. And the final architecture found is not that exciting. It might also be useful, for example, for efficient nets or something. But what's really important is the code for the NAS method, the hyperparameters for the NAS method, the way you found these hyperparameters for the NAS method, the training pipeline, the hyperparameters of the training pipeline, the seeds, even the seeds sometimes make 2% difference. So it's really releasing code means just releasing the whole damn thing. And NAS and HPO, because it's this meta problem, have more hyperparameters because you need the whole inner pipeline and then the outer pipeline. And all of that should optimally be open source. And of course, sometimes you can't open source everything because, you're using some type of parallel compute infrastructure that is just core to the company and can't be released. And that's perfectly fine. But try to really release everything that you can. And typically, the training code for the neural network, like for CIFAR 10, this is just a single file. This doesn't need to be parallelized. Should be actually very easy to be released. And by now, people are also releasing it. Then properly comparing methods using scientific methods, and you can do that using tabular and surrogate benchmarks and reporting important details. Like, for example, hyperparameter tuning is really important. And if you tune on each of your new NAS benchmarks, then yeah, you can of course get good performance, but that doesn't scale to practice. You can't say, well, here's a new search space and a new data set, and the first thing I'm going to do is tune my NAS method on it by in the inner loop running the NAS method a lot. that doesn't work. Yeah, this needs to be reported properly. And so a suggestion to reviewers to de-emphasize the final results on the typical tables of CFA10 performance, ImageNet performance, but rather be aware of these many confounding factors. All right. Yeah, we're really trying to build a scientific NAS community. We have benchmarks now. We have best practice lists. We have run NAS workshops at iClear 2020 and 2021. We also have Naslib that you will be working with later on. This modular and extensible open source NAS library that has most tabular search spaces in there. It also has common black box methods, all kinds of different NAS performance prediction methods that I didn't talk much about, but that you'll see in the hands-on. Several different weight sharing methods, multi-fidelity methods. But if you're excited about this, I think we would love it if other people would also start using it. We have some external collaborators from some companies too already now, but we would love to have more workforce on this. And there's lots that can be done. And yeah, I think this will be the future of neural architecture search because it allows apples to apples comparisons without confounding factors. And many of the weight sharing algorithms, yeah, it's kind of a couple of lines of pseudocode, and you want to actually just change one or two lines in order to make it to the other methods. But right now you have to go from one package to another package and everything changes. And so there's so many confounding factors that are remedied by Naslib now. All right, so that brings me to the end. My takeaway messages are neural architecture search is really coming of age. We're building the scientific community. Where can we find the slides? It's down here at automl.org/talks. There are many ways to speed up NAS by weight inheritance, by weight sharing and one-shot models, by meta-learning and multi-fidelity optimization. And we saw these extensions to joint NAS and HPO and neural ensemble search. So we're forming this NAS community, and I would very much invite you to be part of it. With that, let's get to questions. Thank you.